Okay, welcome back, everybody. So last lecture, right, today the subject is Floquet theory. However, what we had done now during the first two lectures was essentially working through the dress state picture to the James-Cummings approximation. So just to remind you, okay, so the James-Cummings approximation was essentially thought to describe the near resonant coupling between a caricature of an atom, which many people then just call as a two-level atom, right? And which you have to isolate in the experiment, as I mentioned, right? With a quantized mode of the electromagnetic field, a single quantized mode of the electromagnetic field, which is, I mean, equivalent to a harmonic oscillator, to a one-dimensional quantized harmonic oscillator. And then this was done in the case of near resonant coupling, so where the driving frequency omega is roughly equal to the transition frequency to the isolated, to the targeted transition frequency of the atom, which then makes locally this two-level atom, which is this energy distance here, this energy splitting, right? So near resonant coupling. Yeah, and before then, just in the dress state picture, the dress state picture is the picture where we have the Hamiltonian, the Hilbert space, which is spanned by the Hilbert space of the atom, or let's say of the two-level atom. Yeah, tensor the Hilbert space of the harmonic oscillator. Yeah, and then the Hamiltonian was the free atomic Hamiltonian plus the free harmonic oscillator Hamiltonian plus the interaction part, right? And dress states are now the dress states where the states of the atom are the eigenstates of atom and field, right? And then we had written V essentially as some coupling constant, which, I mean, has all the constants which we typically set equal to 1, or which we measure in appropriate units, such as to be able to set them equal to 1. And then also the actually atomic structure, so the coupling matrix elements, the dipole matrix element between the ground state and the excited state. But then the operator valued part of the coupling was sigma plus sigma dagger, which was the atomic raising and lowering operator, right? And then A plus A dagger. And so this was still the coupling between the two-level atom and the quantized mode in full glory, right? And then we took this near resonant coupling serious. And then what did this earn us, this near resonant coupling? So what were we able then, which approximation were we allowed to do under the assumption of near resonant coupling? Anybody remembers? Some people are looking at their notes. That's good already. Yeah. So if you find something, let me know, please. Anybody has a hint? So what was the trick? Yeah? Rotating wave approximation. Bravo. Your name, please, again? Your name? Boyan. Okay. So and the rotating wave approximation, right? That's what we do then, right? So, but why could we do it? So we observed something. Let's say when we integrate, so we went to the interaction picture, right? Then we saw that the dynamics is generated only by this coupling term. Then we integrated this, right? And then we saw that there were time dependencies which were oscillating with before the rotating wave approximation. Do you remember how these time dependent terms looked like? I mean, look in your notes, right? So it's fine if you have notes and there is something useful in there. If there's some information stored in your notes, okay, so which you can extract, right? If it's a complex system, so then, for example, my handwriting is a complex thing, so it's not so easy to decipher information. So now, what do you find there? Okay, so I write it down. So there were these terms exponential, right, of plus minus I, and then we had terms omega minus t, and then we had terms exponential plus minus I and omega plus omega t. Right, and now you see that in this case that these frequencies are close to each other, then this term evolves on a different very different time scale than this term, right? And so there's the separation of time scales. Right, which then allows to do the rotating wave approximation. Okay? So the important step is near resonance condition, separation of timescales, also known as secular approximation or whatsoever which then gives rise to the rotating wave approximation, which in other contexts is also known as the secular approximation, right? And so then this tells you these are much slower than those ones, and so you just, you suppress this one because these on average will have a small or a negligible effect, right? So now this was to say that what we have done so far, right? So now rotating wave approximation, RWA. So then we get V Jaynes-Cummings, right? Is then only G times sigma A dagger plus sigma dagger A. Where you also say from time to time that you keep only the energy conserving terms of the interaction Hamiltonian or interaction part of the Hamiltonian, right? So, but now this, which is in some sense the guinea pig for people who try to build quantum computers, right? Because anytime you read a new paper in typically one of the nature journals, right? When people say we have a new platform for building a quantum computer, I mean, these is always these promises, right? And 10 years later, nobody remembers anymore because still 10 years later it doesn't work. But anyway, so whenever they write their first paper, they essentially showed you that they can realize the Jaynes-Cummings coupling in these systems, right? And then you see these Rabi dynamics, which we saw, which are then associated with what this community calls strong coupling, right? So this is the community. So what we did in the first two lectures is essentially, if you wish, so the paradigm of CQED, yeah, cavity quantum electrodynamics, which then allows the control of the dynamics of single qubits, so dynamics of a quantum state on the Bloch sphere, which is one of the cornerstones of building a quantum computer, because a quantum computer is composed of a register, or is living on a register of qubits, right? So that's therefore the elementary step. However, all these approximations strongly are hinging on this separation of timescales and on this near resonance condition, right? So while the world is of course larger, so first there are different atoms, there is much of atomic structure when you do molecular physics or just atomic physics with real atoms, right, which can ionize, for example. And of course there is more complicated configurations of the field, right? And so it's generic that you cannot make these assumptions, so that you cannot describe the system with these with this Hamiltonian or with this coupling. And just to name some other fields which are also very prominent, where you also read where you get tons of nature papers, right? So for example, there's attoscience, there's the large field of attoscience. Yeah, so atto means you essentially, rather than, you see here, we always implicitly assume that we have a well-defined frequency. So this means essentially what the experimentalists would call coherent wave. So you have a coherent wave which has a well-defined frequency and it's just oscillating all the time, right? While attoscience is light-matter interaction with ever shorter light pulses, right? Light pulses of the duration of an attosecond, right? And why an attosecond? Because the attosecond is typically the timescale on which the electron in the ground state of the hydrogen atom circles around the nucleus. So it's like when you want to take snapshots of the motion of something, right? For example, you might know these old YouTube videos which show when people tried to decide whether a galloping horse is having at times all the four legs in the air. So they had to do they needed a camera and they needed to snapshot this, right? And so they needed short exposure time. And now you don't want to take movies of horses anymore, but you want to take movies of, for example, of electrons in motion close to the nucleus, right? And so you need atto pulses, right? And so this is closely connected to the domain of high harmonic generation, high order HO HG. Anybody who saw this? I mean, who saw this acronym already? Okay, so it's high order. So it's high order harmonic generation. Yeah. And there what you do essentially, now if you have a real atom, which typically has this vector structure, so here you have the continuum, so the free electron states, right? Here you have the Rydberg series, and here you have the ground state. So typically what you do, then you do a transition, you drive a transition with many, many photons, etc., into the continuum, right? And you see that typically these photons are not near resonant, right? And yet you see quite dramatic effects, right? So therefore, it's clear that we need a formalism which goes beyond what we have done so far, just despite the fact that this, in a certain realm, in a certain in a very small subset, actually, of the entire parameter space which describes light-matter interaction, is very successful, right? And so high-order harmonic generation, this was done first, right? And then people, I mean, saw that these atoms which are strongly driven by these pulses emit high harmonics of the injected radiation, and these different high harmonics, they are actually mutually coherent, and therefore you can then, they also emit short pulses which are attosecond pulses, okay? And now to describe such type of physics, now you can do different things, bless you. So you can, I mean, let's say either you just, the first thing you can do, you can relax the near resonance condition, so you just would carry along your anti-rotating term. So you would, I mean, these time evolutions would not be representing separating timescales anymore, right? Welcome. But so you have to take, you must not discard either of them. And so you might stay within the dress state picture, but then you would still have to, I mean, enrich your atomic structure, right? And now, since in this field often actually you are not dealing with quantized field but with classical laser fields, so therefore you do something which is called a semi-classical approach in light-matter interaction. So semi-classical variant of the dress state picture Now, what do you associate with the term semi-classical? Semi-classical. So we're doing quantum physics, right? So, and we have essentially 2 degrees of freedom, right? So the atomic degree of freedom, right, which may have many electrons, so there's many degrees of freedom, but let's say we lump them together, so we say the atomic degree of freedom, and the electromagnetic field's degree of freedom. So these are 2 degrees of freedom, and we did the dress state picture where both degrees of freedom were quantized. So we have 2, both of them were quantized, so it's a fully quantized picture. And semi, that's actually Greek, this means half, right? So we take a picture where half of the picture is classical and half of the picture is quantized, is fully quantum. And so semi-classical means that we take the matter degree of freedom, DOF, degree of freedom, right, is quantized. And the field degree of freedom, DOF, is considered classical. Yeah, so as a classical, I mean, light wave, right, which has a well-defined frequency, a well-defined amplitude, etc. So, and semi half the system is described classically, right? And so now this, right? So this semi-classical variant of dress state picture, that's the Floquet picture. Yeah? which, okay, we'll see. So this is something which is, I mean, enormously powerful actually in the description of light-matter interaction, irrespective of the, essentially of the strength of the drive, right? Or of the frequency of the drive. So we do not need to make any of the approximations or assumptions which we needed to derive the James-Cummings Hamiltonian. Of course, then, in principle, the formalism will be a little bit more bulky, but you will see that at least at the beginning, it also looks quite elegant in some sense, right? And so that's what we're going to go after now. So now I dive into the formalism. And maybe let me give you two pieces of literature which I can recommend really very, very much, right? Okay, so there's one which is the original paper by Floquet, which is in French. I mean, who speaks French here? Okay. So look, I mean, I'm still trying to learn some words of Chinese, but it's much harder than French. So I can tell you it will be much easier for you to learn French than for me to learn Chinese, okay? So, and now here's a good reason to learn French, right? So the original paper is by Gaston Floquet. And this was, actually, he was a mathematician, right? And the title of the work is on linear differential equations with periodic coefficients, right? So essentially, he was a mathematician. He was interested in the solutions of linear differential equations with what we would call periodic boundary conditions, okay? So this was in the Annales Scientifiques of the École Normale Supérieure. And I mean, volume 12, page 47, 1883. So you see it's actually old stuff, right? But then it was mathematician, and typically physicists, of course, it takes them some time to realize what mathematicians have done, that they do something useful, right? So this, however, is very useful because so now we will be looking at something where an atom is driven periodically in time, right? So we will have a translation, a discrete periodicity of the Hamiltonian in time. But is there any other scenario in physics which you might have already encountered where you have Schrödinger equations which have periodic boundary conditions? Where? So where do you see periodic boundary conditions in physics? Else than here when you periodically drive a system in time. Lattice, bravo. Yeah. So when you want to describe the, for example, the theory, or you want to formulate the theory of electronic conductance, right? So then you have periodicity in space, right? And this is also, and then this comes with which theorem? There's a theorem which is also famous, which then tells about the eigenstates of an electron on such a spatially periodic lattice. Bloch theorem, right? So let's say also Bloch theorem, right? So now this, right? So this has now what is known as the Floquet theorem, right? Which is often quoted in the context of periodically driven system, but the Floquet theory originally is actually also the basis of the Bloch theorem, right? Yeah, because the mathematician, of course, doesn't care in which space you go periodic, right? So just would tell, I mean, wherever you want to go periodic, I give you this theorem, right? So this is one point, and then the other paper is actually, and this now is in English, and it's a very, very useful paper if you want to get basic introduction to Floquet theory. It also, in particular, it deals also with the special case of a two-level atom. So it works out then again the special case of the two-level atom under periodic driving. Right, and this is the paper by Shirley, J.H. Shirley. This is in Physical Review, and this is still, I mean, it's still the old. I mean, it's 50 years or 60 years old, right? So it's when they still had a different nomenclature. So it's volume 138. And then the B series, which labels the page, so it's B979 and 1965. Yeah, and both papers are actually, I mean, when you Google them, you find them online, right? Open access. And this really, I mean, it's a, yeah, so if you, I mean, want to read up stuff, which I'm doing now with more time, right? And also with, I mean, expanding beyond what I'm doing now, and also relating actually to the Jaynes-Cummings model in a certain perturbative limit, then look at that. It's really a very, very useful reference, okay? Okay, so now let's start with the formalism. Okay, so formalism. So we consider the following Hamiltonian, right? H, given again by the unperturbed Hamiltonian, which we already have diagonalized, plus f z cosine omega t. Right? So now remember, so first remember that this is, in my handwriting, this is an F, it's not plus minus, it's an F, right? It's the amplitude, the strength of the driving field. That's the dipole coupling, that's the time dependence of the drive. I measure the electronic charge in units of the electronic charge, so I set it equal to 1, right? And that's the Hamiltonian we are going to deal with, right? So now you see, in contrast to the Hamiltonian I wrote down in the stress state picture, there I had written down the atomic Hamiltonian, then the free Hamiltonian of the field, so the potential and the energy of the harmonic oscillator, and the coupling, right? Now here, this is just the atomic Hamiltonian, so, or the matter degree of freedom, which will typically be an atom, or a molecule or whatsoever, or a solid state object, as you wish, right? But I know that its eigenstates and eigenenergies, and now I drive it. But now what is missing is the energy of the field. I only have the interaction part. So what does this already imply for my, I mean, so this actually implies an approximation. Despite the fact that I was saying actually it's essentially approximation free, but if we are very, very strict, it implies an approximation. Right, so I say I don't care about the energy of the free field, right? And so this means that the interaction between the atom and the field will essentially not change the state of the field. So any let's say the typical number of photons which are, either absorbed from the field by the atom or spit into the field by the atom, right? They do not really change. It's a small number of photons with respect to the total number of photons in the field, right? So that's an implicit assumption, but that's of course, it's also not surprising. That's what you would often see as a structure in elementary quantum mechanics courses when you, for example, were to take a perturbation here which is not time dependent, right? And so now we assume that H naught be already diagonalized. So, oops. So H naught alpha equals E alpha alpha. So that's the eigenstates of the unperturbed Hamiltonian. They can be discrete or continuous, right? Discrete, plus perhaps continuous spectrum. Yeah. And we have the period of the drive. So the Hamiltonian is periodic. H of t plus t equals h of t, right? With t, in this case, equal 2 pi over omega, right? But note now that actually this is a specialization for this type of driving. Right now here I assume, harmonic driving. But in principle for what I'm going to write down, the naked formalism, I only need this periodicity, right? So it could also be, for example, a sequence of delta pulses which come just, for example, you put a hammer and in periodic way you just put a delta kick or a sudden impulse you apply a sudden impulse upon your system. This would also do because still you would have this periodic structure of the Hamiltonian, right? So that's what we need. This periodic boundary condition now here in time. And And then now the Floquet theorem, I state now the Floquet theorem, maybe I state it here. Let me see, I don't know, okay. So Floquet theorem says there exists a complete and orthogonal or orthonormal set of eigenfunctions and I will have to say eigenfunctions of what, right, of which operator? Eigenfunctions, and I write them as epsilon of t. Yeah, so it's plausible, right? The Hamiltonian, the potential which the atom sees, which the target sees, right, is periodic in time. So it's plausible that the solutions must also be time dependent, right? And actually, these are now living, these epsilon of t, which are now the semi-classical analoga of the eigenstates of the dress state picture, which we dealt with so far, right? They are living in a tensor product of L2, which is the space of square integral functions, right? Tensored with the unit sphere. So this is the unit circle. Yeah, and this represents the time periodic functions, time periodic with period capital T, right? So these are the. So this is the standard Hilbert space in which you're typically living when you do quantum theory of time independent systems, right? So standard Hilbert space. Yeah, where square integrability just is, summarizes that you want to have a proper probabilistic interpretation. And here's the unit circle, so that's the time t periodic functions. Yeah. And so now I have to continue the sentence. There exists a complete and orthonormal set of eigenfunctions. Of course, when I mean complete and orthonormal, I still have to will have to specify also the scalar product, right? Apparently on this space, right? Such that e to the minus I epsilon t times epsilon of t, where I still have to specify which is these epsilons here. I mean, I just now write that they are real, epsilon real, and linear combinations thereof solve the Schrödinger equation. And now, okay, I just now write, for the sake of time and space, I just write SE for Schrödinger equation. Solve the Schrödinger equation. I dt psi equals h of t psi. Yeah, so the Floquet theorem gives us, right, a family of orthonormal states, epsilon of t, right, which I can combine with prefactors e to the minus I epsilon t and constant expansion coefficients, such as to write any solution of the Schrödinger equation generated by this time periodic Hamiltonian. Okay, so that's the for the photo. Maybe for taking photo documentation, maybe it's better like this, right? Right, and the epsilon, no, this I should write still there, so for you to have it complete. the epsilon are the real quasi-energies associated with epsilon, with the epsilon of t. Okay, so I will have, I mean, as many as I have dimensions of my Hilbert space, right? Of these epsilon of t, so I have correspondingly then these associated quasi-energies, and then I can write any solution of the Schrödinger equation as an expansion in these vectors here with constant expansion coefficients. And this I will now write down after I clean the board. Or you can let this sink a bit. Okay, so this means, right, as I said, right, so any solution psi of t of the Schrödinger equation can be written as, so then, I mean, let's say I still have these constant expansion coefficient to take care of the initial conditions, right? So psi of t I can write it as sum over epsilon, which are the quasi-energies or the quasi and the associated eigenstates, c epsilon e to the minus I epsilon t epsilon of t. Right, and now you see that here I said that the epsilon are the real quasi-energies associated to the epsilon t, and to the vectors epsilon t, and I call them eigenfunctions, or eigenfunctions of what? And as a matter of fact, they turn out to be, so epsilon of t are eigenvalues and eigenvectors of the Floquet eigenvalue equation. Yeah, which I had written down already last time, which is h minus I dt. Now, so I set h bar equal to 1, or I measure actions in units of h bar, right? Bless you. So to get rid of that, so epsilon equals epsilon. Yeah, and actually we will see this in a minute, that this actually drops out from, plugging this here into the standard Schrödinger equation, right? And when you do that, you get this, okay? So and solving, so the constructive recipe is you write down your Hamiltonian, right? You subtract this IDT, right? And then you solve this eigenvalue equation. Now, which is the structure? Remember what I asked you last time at the end of the last lecture. I asked you to contemplate a bit whether you think that this here, is closer to a time-independent eigenvalue problem or a time-dependent eigenvalue problem. Because often you read also in the literature that people say, okay, now I do Floquet physics, so I really consider time-dependent quantum mechanics. So now, given this structure, would you say that this is a plausible statement? So how do you call the structure of an eigenvalue equation typically in quantum mechanics? look, I mean, typically you have something like I dt psi equals h. Now I put h naught, right? So because psi, and then you also have h naught psi equals e psi j. Right, this you know, right? So then here you call this is the time-dependent Schrödinger equation, and how do you call this typically? Yeah, the stationary Schrödinger equation, right? So it's the, I mean, let's say, you say, I mean, here you say precisely this, right? So the statement is, I mean, you can write down any solution of this Schrödinger equation given that h naught is time independent. You can write it down as a superposition with time-independent coefficients of the eigen solutions of this eigenvalue problem, okay, which is the stationary of the stationary Schrödinger equation, right? And you see now that here, now we have a time periodic Hamiltonian, right? And we see that we can actually solve, we do precisely the same. We can write down any solution of the Schrödinger equation generated by this time periodic Hamiltonian, right, as a linear combination with constant coefficients of these objects, yeah, which I get by diagonalization of this object here. Just diagonalization of this object here now on, right, on L2 tensor S1, right? So therefore you get a stationary, this is a stationary eigenvalue equation, right? So this is a stationary eigenvalue equation just on a space which is enlarged by this tensor factor here, right? And so it means that actually T now in this picture takes the role of a generalized coordinate, right? I mean, the time now becomes something like a generalized coordinate, so you can conceive the Floquet picture as a time-independent problem just in an expanded space, right? And this actually has a deeper reason which I cannot expand upon now for reasons of time, but this is important. This is something I want you to carry away, right? So you have to realize that the entire, how shall I say, beauty but also usefulness of the Floquet picture hinges on the fact that you can plug it into the structure of a time-independent problem. And remember also that now again with the Jaynes-Cummings Hamiltonian, right, what we achieved there after the rotating wave approximation was also that the Hamiltonian became time-independent, right, because we assumed that capital omega equals omega. Hence, the terms exponential I times capital omega minus small omega times t, when capital omega equals small omega, gets just unity, right? So therefore, the Hamiltonian becomes effectively time independent, right? While we threw the counter-rotating terms away. Now here we do not do anything like this, and yet we get a stationary structure, right? So it's a much more general framework, and in this sense, much more powerful, right? So, okay, and now just to see that, right? So to see this, right? So you plug to see this, yeah, e to the minus I epsilon t epsilon into I dt into I dt psi equals h psi, right? So we replace this here for psi into the Schrödinger equation, which is generated by this time periodic Hamiltonian, right? And so I get I dt e to the minus I epsilon t. Recall that I I get rid of h bar by setting it equal to 1, right? Times epsilon of t, right? Now I have to, first derive this and then derive this, so I get sum, right? So first I get the epsilon down, so I get epsilon e to the minus I epsilon t epsilon of t plus e to the minus I epsilon t I dt epsilon of t, yeah, equals right-hand side h e to the minus I epsilon t epsilon of t. Yeah, and now you can just, divide out the e to the minus I epsilon t, because this has to be true for all times, right? And so then you see here you have h, now you bring this to the right-hand side, so you get h minus I dt equals epsilon times epsilon of t, right? So I do this, I do chain rule, I get epsilon times this, plus e to the minus I dt now acting upon this, and the right-hand side is this, right? So now I get rid of those. So I get rid of those, right? And then I have h. Now I get this on the right-hand side. I get h minus I dt acting upon epsilon of t equals what is left on the left-hand side is epsilon times epsilon t. And this is what we have here. Okay? So now, okay, some quick observations. Well, I don't write them down now for reasons of time, right? But let's say one of the observations is that this is a stationary eigenvalue problem. Right? On a larger space. And then the statement in these expansion of any solution in terms of the thus obtained eigenstates with associated eigenvalues with constant coefficients is just the same statement you have in the case of autonomous Hamiltonians, where you get also, I mean, the function system then by solution of this stationary solution, right? Or stationary equation. Okay. Good. So now then we will carry a bit further, right? So the first thing now is to I mean, still maybe you see when you see this, it looks a bit strange still. So one doesn't really, I mean, to treat this as a position coordinate is a bit strange, right? But now we make a few steps how to plug this then really at the end into a matrix equation. Right. So now, Yunan, I have to ask. And I have to ask you, how much time do you still give me before you, I mean, die because you need lunch or because it's too much? I mean, because I'm just talking too much. So how much time? 20 to 30 minutes. Is this okay? Say it. Huh? Okay. Thank you. So the first thing is, let's say, the last statement of this I could put here still. So the epsilon of t, right? They inherit this periodicity of the drive. Okay, so this you can also put as an additional statement in the Floquet theorem. But it's coming from this periodic time boundary conditions, right? And so therefore you can also write the epsilon of t. You can actually expand them in a Fourier series, right? So you can write them as k equals minus infinity to plus infinity as e to the minus I k times omega times t times epsilon k, right? And now here comes this, and you see here now, this is in some sense a superposition, right, of states which are living on the unit circle and states which are living on L2, right? So this is L2. See above, right? So we have solutions which are living on this tensor product of the unit circle and of L2. And this we will need later, right? So now the first thing which this gives us, right, is that the periodicity of the Hamiltonian in time, on a time axis, implies the periodicity of the spectrum, of the Floquet spectrum, right, of the spectrum of these eigenvalues epsilon on the energy axis. Yeah. And to see this, we do the following. So to see this, define the state epsilon plus k omega of t. Yeah, so now I mean I know what epsilon of t is, right? This is one of these eigenstates up there, right? Eigenstates which are obtained by solution of this eigenvalue equation, right? And now I introduce a new object which I call epsilon plus k omega of t, right? Which I define as this epsilon of t garnished by e to the minus I k omega t, sorry, by plus e to the I k omega t. Whether you take plus minus here, it doesn't matter. I mean, let's say you just have to be consistent. So here, but here it shows plus, right? And so now you have what you first want to show is that also this solves the Floquet eigenvalue equation. Okay. So now I'm to see this, define this, yeah, and observe, yeah, that. Now, IH minus I dt, this is now the left-hand side of this, right? Applied now on this one, t equals now by this definition, H minus I dt, e to the I k omega t epsilon of t, and this now gives me, I mean again here I get from application of the I dt upon this product, right, I get first something like k omega times this plus e to the I k omega t times I dt acting upon this, right, and then of course I get the terms in H. So if I write all this down, I get, so I just, maybe I start there. So I get H e to the I k omega t epsilon of t plus, now from application of this upon this, so plus k omega e to the I k omega t epsilon of t minus, this comes now from the, I write it like this, e to the I k omega t I dt epsilon of t. Right, so first just H and then the action of this on this product. So I do the product rule again. And now this by use of the, so here I have e to the I k omega t times H minus I dt on epsilon of t. So there I can, then this I can replace by epsilon on epsilon of t, right? So I get e to the I k omega t epsilon times epsilon of t. So these were essentially, this was essentially this term here, and this term here gives me this term here, right? And then plus k omega plus e to the I k omega t k omega epsilon of t. So on this, and this then is equal to, so this gives me epsilon plus k omega times e to the I k omega t times epsilon of t. Times e to the I k omega t epsilon of t. And this, by the definition of this new object, epsilon plus k omega of t, being defined by that, okay, gives me epsilon plus k omega times epsilon plus k omega of t as a ket. Right, and so this means that now this new object is again, solves again the Floquet eigenvalue equation, just with an eigenvalue which is shifted just by an integer multiple of omega, right? Now, however, now if you now take these, if you now take these guys to expand to write down an arbitrary solution, the same solution of the Schrödinger equation, which you could write down with the epsilon of t originally, as originally formulated in the Floquet picture, right? So now the shifted solution, these shifted solutions, by plus k omega, right? Yes. The shifted solutions produce identical solutions of the Schrödinger equation. Meaning, if I were to take the representation of a given solution in terms of the epsilon of t, right? And I replace all the epsilon of t by the epsilon plus k omega of t, I get the same psi of t, okay? So produce identical solutions of the Schrödinger equation. And this you see by just writing that. So psi of t equals sum c epsilon, right? So that's by the original statement, e to the minus I epsilon t, epsilon of t. And this now you just write, you plug in just here a e to the minus I k omega t, and you compensate it by an e to the I plus k omega t, right? So you can write this as c epsilon as e to the minus I epsilon plus k omega t, and now you have to compensate this one here, right? This one by e to the I k omega t, epsilon of t, right? And this is sum over c epsilon e to the minus I epsilon plus k omega t, and now our new objects, the shifted Floquet eigenstates epsilon plus k omega of t. Right, so given epsilon of t as a complete set of solutions of which give you arbitrary solution of the Schrödinger equation generated by this periodic Hamiltonian, you can construct other sets of equivalent eigenstates which are just shifted on the energy axis by k omega, right? Because here they fulfill the Schrödinger equation, this Floquet eigenvalue equation for another eigenvalue shifted from the original eigenvalue by k omega. So this means there's a certain redundancy in the spectrum of your Floquet Hamiltonian when you take it over the entire energy axis. Okay. So this means redundancy of entire spectrum. Yeah, and what the mathematicians call is a rest class structure. Rest class structure. Yeah. And this means that it suffices to take the solutions of the Floquet eigenvalue, to take only those solutions of the Floquet eigenvalue problem which lie within a spectral interval of length omega, right, which is called then the Floquet zone. Okay. And so in some sense, now when you have the energy axis, I will chalk down something a little bit more in detail, but now just to give a first picture, and then you can contemplate this already a bit, right? So in principle, you have here the energy axis, energy. Yeah, you find some eigenvalue epsilon here and an associated eigenstate. now assume, let's say, now assume that, I mean, omega on the energy axis, right, where energies and frequencies are now taken identical because just energy is just h bar times the frequency. H bar was set equal to 1, so therefore we have just frequencies, right? So now if this is omega, right, so then there will be a second interval of length omega, right? And so therefore you know now that you will find another eigenvalue, which is essentially now here this one. This would be epsilon plus omega, right? And this is now the two eigenvectors which you find associated with this one and this one. They contain the same information, right? And they contain the same information because they have Fourier coefficients, right? Which now just have to be labeled, are labeled differently. So you will find epsilon of t and epsilon plus k omega of t will essentially be the same beast, right? Just with these epsilon k, or these expansion, I mean the L2 part of the expansion, of the Fourier expansion, sitting at different values of your label k. Okay, so that's a bit, that's not so easy. I mean, let's say this is something to chew upon a bit, right? But I will make a drawing now. Okay. So again, here's the energy axis. Let's say now here. This is omega. Omega. So that's also called then a Floquet zone, right? So this is also called a Floquet, which in the Bloch theorem, in the Bloch language, how will you call that? Brillouin zone, right? Yeah. So, and now you imagine that at least at all these, now assume you have an eigenenergy here and its replica essentially here, right? And you can imagine now if you expand the eigenstates epsilon of t as e to the minus I k omega t epsilon k, right? So these are, now you have to imagine, essentially you have, I mean, your Hilbert space is now labeled, I mean, the entries in your, if you write this as a vector, right? You have labels k, right? And then you have the quantum numbers which, I mean, which expand this expansion coefficient here in the basis of your L2 part of the Hilbert space, in the L2 basis of your Hilbert space, right? So you have quantum numbers here, and you have the quantum number k here, which represents the degree of freedom of the field in the conjugate variable, which is the frequency. And so you can imagine your eigenvectors as, I mean, given as vectors in your basis, which is spanned by these functions and the eigenfunctions of your L2, right? And then you essentially can imagine that these, yeah, so k goes from minus infinity to plus infinity, right? So here this is epsilon of t. Yeah, and now here you have the same I mean, you have the same information stored here in this eigenvector, right? And again, this is your, I mean, that's the k index, k index. And now if you take, for example, this one, you assume this is epsilon of k, epsilon k, for this vector at eigenvalue epsilon, right? Then this will be shifted essentially into this block for the eigenvalue. Here you have epsilon plus omega of t. Okay, just to get, so this is then essentially epsilon k, which is garnished here by the factor e to the minus ik omega t, and here it's garnished by e to the minus ik minus 1 omega t epsilon k. Okay, so that's a little bit of the accounting. So when you do real, let's say computations, and you do put this on your computer, you have to think a little bit about this. But in principle, you just, if you were to only take the information within one Floquet zone, right, then you need not, make nodes in your brain with transporting this along the energy axis or across different Floquet zones. But that's what you have to keep in mind a bit. Okay, so now. Okay, I don't say anything anymore now in detail about the orthogonality of these states. So essentially, I just state now. You see that you're on a larger Hilbert space, right? So you have now to define your scalar product by essentially a combination of the scalar product, which you know from L2. So for these guys, right? And then you still have to account for this time periodicity here in the expansion coefficients, right? I mean, along to account for the time-dependent part of your solutions, right? And so then this part of the scalar product will be then an integral over one period of the drive. But this you can look up in the Shirley paper. So now, just for reasons of time, to finish at half hour, I just want to give you now an explicit representation of the Floquet eigenvalue problem h minus I dt. Epsilon equals epsilon epsilon as a matrix, right, expanded in the eigenbasis of L2 and with respect to the k index, right, which represents the harmonics of your driving field. And for this now we go to the specific representation of the Hamiltonian, which was this h naught plus cosine omega t, so with this harmonic driving, which is a special case, right, but which then allows for a nice representation. So let me see. So I have to shortcut a bit. Yes, let's take the following. Okay, now we start from this. And now we plug into this epsilon, again, this expansion of epsilon as a Fourier series, right? So we write h minus I dt. And now we write sum e to the minus I k omega t epsilon k, right? This is just this in its Fourier representation, k running from minus infinity to plus infinity, right? And so I get first, I multiply h in, so I get sum over e to the minus I k omega t h acting upon the L2 part of the Floquet state, right? Minus, and then I get this upon this is the time dependence here now. The time derivative acts only upon this because this is the time independent part, right? So I get just simply minus k omega e to the minus I k omega t epsilon k. And now I get concrete. Now I make the periodicity of the drive, or the periodic part of this Hamiltonian here explicit. I replace it by cosine omega t. So I write with h equals h naught plus cosine omega t. I write now sum over k. e to the minus I k omega t, now h naught, acting upon epsilon k, yeah, and now plus and now I write the cosine in this Euler representation as a sum of e to the I omega t and e to the minus I omega t, right? Times 1/2, right? And then remember the coupling was F, the strength, the amplitude of the field, times Z, the dipole, right? Times the cosine, right? Sorry, it's missing here. Yeah. So I get plus F times Z, now halves from the Euler representation of the cosine, right? Times e to the minus I, now k plus 1, yeah, plus 1 times omega t times epsilon k, and then plus fz halves e to the minus I k minus 1 omega t epsilon k, right? So this is now just this part here, right? And then I still have this part, which is the minus k omega minus k omega e to the minus I k omega t epsilon k. And I close this parenthesis here, right? Right, and then this is equal to, I mean, epsilon times sum over e to the minus I k omega t epsilon k, which is the right-hand side of the Floquet eigenvalue equation. Now this has to be true for all times, so therefore I can take the coefficients of these e to the minus I k omega t to vanish independently, right? And so therefore I get actually h naught times epsilon k plus fz halves epsilon k minus 1, right? Because I have to take, I mean, I have to take the coefficients of all e to the minus I k omega t in the sum the same, right? So therefore I have to change the index here, because this here, then I have to take, if I want e to the minus I k omega t here, I have to lower k by 1 here, and I have to increase it by 1 here. Right, and so I get plus fz over 2 epsilon k plus 1 minus k omega, and now the right-hand side of the eigenvalue equation is epsilon k. And this now for all k in z, because the sum is running from minus infinity to plus infinity in this Fourier representation. Okay, so now I do the following definition. I define a new lowering and rising operator now, which is reminiscent of what we know from the dress state picture or from the harmonic oscillator algebra. So I define epsilon k acting upon epsilon k to give me epsilon k minus 1. So to lower the expansion coefficient in the Fourier representation of the Floquet eigenstates by 1, right? And a dagger acting upon epsilon k such as to increase the expansion coefficient by 1, like this, right? To obtain the following form, h naught of this eigenvalue equation now for the epsilon k, right? H naught plus fz halves a plus a dagger times epsilon upon epsilon k equal epsilon plus k omega upon epsilon k for all k. Yeah, and this is now the explicit representation of the Floquet eigenvalue equation for the specific harmonic driving which we have used in our Hamiltonian, right? And which now is made explicit in terms of the basis functions with respect to the time periodic part of your solutions, right? and which still has to be made explicit with respect to the expansion of these time-independent parts of the eigenfunctions in the basis of L2 of the time-independent part of your Hilbert space, right? And so, but you see now that if you were now to replace Z by sigma plus sigma dagger, right? You were back in the structure of the, we would be back in the structure of the Jaynes-Cummings, or of the precursor, if you wish, so of the Jaynes-Cummings, of the dress state picture, right? Just that here A and A dagger have a slightly different meaning, right? And now, so last thing is just some picture. So now, if you do now this as in matrix representation, right? So these are the epsilon k, so that's the k components of your eigen solutions, which are the individual blocks here, right? Right? So now, the matrix has the following form. Let me see. Okay. Yeah, so on the diagonal, right, you have H naught minus, you can also put this now, you can put now the diagonal part to the left-hand side, so you would have H naught minus epsilon minus k omega, right? On the right-hand side, or sorry, on the right-hand side you would have this coupling part. So the diagonal part now of the Hamiltonian is H naught. Let's write it differently. So H naught minus k omega plus Fz halves times A plus A dagger epsilon k equals epsilon k. Let's write like this, right? So now you have on the diagonal, now you have H naught minus k omega. So now let's, for example, I put now H naught minus 2 omega. So then H naught minus omega, H naught plus omega, H naught plus 2 omega, and so on, right? So in principle, this goes from minus to plus infinity, right? And then you just have, you see that you only couple to epsilon by definition of A and A dagger. You just only couple in K. You only couple to the nearest off diagonal, to the K plus or K plus or minus 1 off diagonal. So you only have these blocks filled here now. Yeah, and all of them have essentially Fz over 2. So all of them have just this Fz over 2. Fz over 2, 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 and Fz over 2. And now you go from minus infinity to plus infinity. Of course, in your computer you have to stop somewhere, right? And you have to converge it essentially. So you have to make this larger and larger until you see that your results converge. So there's a Fz over 2 is missing here. Yeah, and all the rest is 0. Yeah. So that's now the, and now let's, as a very last step, let's look at the, so this is the Floquet Hamiltonian. In matrix representation for this harmonic driving. And now homework, okay? Homework. Now do the same. Remember our Hamiltonian, which is H atom plus H harmonic oscillator plus H bar G sigma plus sigma dagger times A plus A dagger. Right, this, you remember, this was what we did last time before we got, reduced this with under resonant driving to the Jaynes-Cummings Hamiltonian. Now, if you write this in the dress state basis, so now in N, G, and N, E as the basis states of your harmonic oscillator tensor two-level atom Hilbert space, right? Then you get the following structure. Okay, so then you get essentially, let's say, how do I do that? Yeah, so now let's start here, right? So you get essentially, now I start from the ground state of the harmonic oscillator, right? Because this one has a ground state, right? So you cannot, I mean, you start at n equals 0, n equal 1. So n here runs just through the integer, I mean through the natural numbers, right? While k here runs through all integer numbers. So therefore you start here at the ground state energy E0 j, and here you start at E0 j plus h bar omega, and here E0 j plus 2 h bar omega, and so on. Okay, so I don't continue this here now, right? And then what you see here is that you get, here you will see that you get h bar g sigma plus sigma dagger. Here you get h bar g square root of 2 times sigma plus sigma dagger. And here you get h bar g square root of 3 sigma plus sigma dagger. Yes, right? So now you see that here you have the sigma plus sigma dagger. I said this is the same like the z here, right? And you see now the 2 you forget, the h bar you also forget, because here I set it at 1 anyway, right? But you see that here along the diagonal, the coupling matrix elements change, right? And they are actually, these 3's are essentially the ends of these basis states, right? While here they don't change, right? So therefore, I mean, from this, I mean, let's say of this you have to convince yourselves, because I have not enough time now to do this in detail, right? But this is the structure, and so the essential difference between the Jaynes-Cummings, between the dress state picture, right, and the Floquet picture is that in the Floquet picture, I do not account for the back action of the absorption or emission of a photon by the atom upon the state of the field, while in the dressed atom picture I do, right? Okay, here the coupling is stronger than here, right? While here the coupling is the same as here, right? And so yes, so I think here we should stop. So this is let's say, so what should you carry along, right? So first, the Floquet problem is in essence a time-independent problem, despite the fact that it looks time-dependent, because essentially it can absorb the time periodicity in an enlarged Hilbert space, where then the problem looks autonomous or time-independent, right? This makes the power of the method. It actually has a deeper reason in actually classical dynamics, which I cannot expand upon now, right? And then the second thing is that the Floquet picture is the semi-classical generalization, because you don't need near resonance assumption. You don't need to be allowed to do rotating wave approximation to get something useful, right? The semi-classical generalization of the dress state picture of the two-level atom for arbitrary atomic structures, even molecules, right? And the approximation which is done is that actually the absorption of a few photons or the emission of a few photons in this light matter interaction process does not appreciably change the state of the field. That's the approximation which is in, right? And so therefore it means that you always need to have many, many photons in the state of the field, such that if you absorb 20, 30, 100 photons or so, or you spit, 130 or 10, 20, 30 photons into the field state, which you see and which causes the interaction process, does not change, right? So this structure, this you have to do as a homework. Please, if you have questions on that, I'm still here for 2 days, not tomorrow, but after tomorrow I'm still here, so I can expand on that if you wish, right? So this and the time dependence, and that's it. Thanks very much.